So for this question, what we will have is a solenoid. So your solenoid is the one that we are going to pass a current through. And then your search coil, you will get the induced EMF. So the first part, they said, sketch the graph of the flux density B in the solenoid. Now what they gave you, now just refer to the original graph, the black color, ignore the red one first. The original graph is the current, which is a cost function. So the flux density will follow the same graph as the current because the flux is proportional to flux density is proportional to current. So therefore you just follow back the same graph. So the blue color one, just plot the blue color. Exactly the same as this. Amplitude not same, never mind, because the value will be different, but the shape must be the same. But on the second part, to get the induced EMF, right? To get the induced EMF, you must remember that the magnitude of the induced EMF is equals to the negative of the gradient. So what you got to do is, if this is a cost graph, d phi dt means, by the way, flux and flux density same shape. So even though our equation says the gradient of flux versus time, but since they give me flux density versus time and they're the same shape, it doesn't matter. So the gradient of this graph, that means you got to differentiate this function. So differentiate cos, you get negative sign. Then you put a negative in front, you get positive sign. So the value of the E is a positive sign graph, but make sure it's the same period. So same period up to here. This is from here to here, one period up to here. So make sure your sign graph also period same up to here. So you can start from 0 here, and with 0 here. In between, you mark the 0. Then here's a peak, here's a trough, then you join together. All right? Now, the next part, right, they said, explain, right, briefly describe and explain what happens if, let's say, you're putting in a ferrous core into the solenoid. What happens to the induced EMF, the amplitude, and also what happens to the frequency. So this is what I'm going to tell you. How does putting a soft iron core affect the amplitude or frequency, right? Now, your soft iron core's function is to strengthen the field. So if your original graph, this is, by the way, the flux density in the solenoid. If this blue color is the original graph, if you place a soft iron core, it's going to be stronger. So that means the maximum flux density will shift up to here. So if it's negative, it will go even bigger, more negative, because the magnitude of the flux density will increase. But you'll notice that the frequency of the flux density with time doesn't change, right? Because here is where the current is 0, so your flux density is 0. So if you want to amplify any 0, it's still 0. That's why there's no change. So your frequency will remain the same. So my point is, if you're talking about the frequency of the induced EMF, you must notice that the frequency of the induced EMF must follow the frequency of the flux density, or the frequency of the flux, or the frequency of the original current. Okay, let me tell you why. Even though, right, this is a cos, this is negative, this is positive sign, but these two will always have the same frequency because of the relationship. The magnitude of this equals to negative of gradient of this. Now, so you notice that this side is negative gradient. So you put in a negative, your value are all positive. So negative gradient corresponds to positive value. Positive gradient, put in a negative, so you get a negative value. So every time your gradient is negative, you get a positive value. Gradient is positive, you get a negative value. Therefore, they will always have the same frequency. Do you understand? So because they have the same frequency, when you put in a soft iron core, the frequency of E also unchanged because you did not touch anything. However, what happens to the amplitude of the induced EMF? Now remember, the amplitude of the induced EMF, or the magnitude here, depends on the gradient of this graph. When I drew the red color graph, is the gradient different from the original blue color graph? Yes or not? So is it steeper or less steep than the blue graph? Steeper, right? Not. So if it's steeper, that means the gradient is bigger, so the value of the induced EMF is bigger. So you can tell them frequency of E unchanged, but the maximum flux density is higher. The soft iron cause effect. So the rate of change of flux linkage should be higher. That's the gradient of the graph. So therefore the amplitude of E will be higher. Now the next one is they increase the frequency of the current, but the amplitude of the current didn't change. So you know what I did? In the original graph of the current versus time, do you see that I maintain the same amplitude but it's higher frequency now? Yes. So this is what is happening. All right. So the question is, now that your frequency of a current is higher, wouldn't the frequency of the flux density also be higher? Versus time, the frequency of flux density versus time is higher. So what happened to the frequency of the induced EMF? Also must be higher. Always same frequency. Right? So the first part, you can write down here. You can say that the frequency of E increases to the new value. The frequency of E increases to the new value. Now, what about the next part is what about the amplitude of the ER, induced EMF? Now, do you think, right, since the amplitude of the current didn't change, do you think the amplitude of the induced EMF will change? Now, most people would say there's no change, because they say, oh, amplitude is the same. But remember, your value of your induced EMF doesn't depend on the value of your current. It depends on the gradient of the graph. With your red color graph here, which is higher frequency, is the gradient still the same as the original gradient? No, you still have a steeper gradient. So because your gradient is steeper for your current, your flux density also be steeper. So steeper means definitely you will have a higher induced EMF because the gradient is higher. So that's what many people don't realize. So you can say this, the next part of the answer, you will say that the rate of change of flux linkage is higher. The rate of change of flux linkage is higher. So the amplitude of E will increase. So the amplitude of E will increase. We are going to discuss this question from the part B onwards because we are discussing about Lenz's Law here. So when you want to state Lenz's Law, you can state that the direction of the induced current is in such a way to produce effects to oppose the flux change that causes it. But we want to use the Lenz's Law to explain the part 2. Use Lenz's Law to explain why the input PD and the output EMF are not in phase. So how do I use Lenz's Law to explain it? Now remember, in a transformer like this, whatever induced EMF you have here will come due to the changing flux which is given by your primary coil. So how do I use Lenz's Law to explain why the EMF here and the input PD here are not in phase? So let's look at what happens to the induced EMF. So the induced EMF, according to Lenz's Law, will produce a magnetic field to oppose the change that causes it. That means it opposes the change in flux here. So you talk about the current here producing a magnetic field here to oppose the changing flux caused by your input potential. So you can say this, the induced current in the secondary coil produces a magnetic field that opposes the changing field produced in the primary coil. So therefore the output EMF will not be in phase with the input PD. So example, if let's say the flux here increases, gets stronger and stronger. So let's say this is north and this is south. So when the field comes over this side, so what will happen is this end of the secondary coil will also be north to try to push another field in the opposite direction to this field. So when this field is getting stronger, let's say this is north and it's getting stronger, getting more and more north, then this will also be north to try to oppose it. So that means you have an original EMF here that is pushing field this way. The EMF here will be opposite because it's going to push the field in the opposite direction. So therefore you will have the EMF which will be not in phase with this input PD. Now for the next part, we're going to use Faraday's Law now to explain why the output EMF here, all right, or the output PD here, or the PD across the load remains the same thing, why it is not in phase with the EMF of the supply. So it's a different approach from using Lenz's Law. So in Faraday's Law, we talk about the induced EMF here is proportional to the rate of change of flux here. So what we can say here is the induced EMF is proportional to the change in flux, not proportional to the flux. You see what's the difference? The flux in your primary is proportional to the EMF in the primary. But the EMF in the secondary is not proportional to the flux in your primary, rather it is proportional to the rate of change of flux, which means like how the flux changes. So therefore, the induced EMF cannot be in phase with this EMF at the primary. So this is what we say: the magnetic flux in the primary is in phase with the EMF in the primary coil, but the induced EMF in the secondary coil is proportional to the rate of change of flux linkage. So the EMF of the supply is not in phase with the PD across the secondary coil. Now for this question, we are given like a transformer, but the current in your primary coil actually varies according to this shape. So your job is to plot how the EMF in the secondary coil would look like. So remember, from the formula E equals to negative dN phi dt, the rule is that the induced EMF value, which is the E, will be equals to the negative of the gradient of this graph. Now, why gradient of this graph? The current in your primary and the flux density in your primary and the flux in the primary will all be the same shape because they are directly proportional to each other. So how do I know that? Because from the formula B equals to mu n I, your B is directly proportional to I, and also from the formula flux equals to BA, your flux is proportional to B as well. So all these three will have the same shape. So therefore, from this equation, dN phi dt means the gradient of the flux versus time graph. Negative gradient of it gives you the value of the induced EMF. So if they give you current or B or flux, doesn't matter. We can use the gradient of this graph, put a negative in front, and that becomes the value. For example, for this first portion here, the gradient here is 0 because it's a horizontal line. So the EMF will also be 0. The second part, the gradient here is less and less positive. So we put a negative in front, so it becomes less and less negative. But don't forget, it is the value of E which is less and less negative. So you start off from a very negative value of E and becomes less negative. So you can go straight to a very negative and then you become less negative value, not gradient, value. So you can actually make a straight line as well, it doesn't matter, or curving this other direction as well, because either way your value will be less and less negative, so it's fine. And then the third portion here, the gradient is 0 because it's a horizontal line, so therefore your value is 0. And the last part, the gradient here is constant and negative, so you put a negative in front, becomes constant and positive, so the value becomes constant and positive. And then the last part here, the gradient is 0, so the value will be 0.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.